meeting is now being recorded.
So, good morning everyone. Welcome to the EeB-CA2 Materials webinar. So just a short reminder, but I see our participants were already attending the last webinar, so I will go quite quickly through my introduction. Just to quickly remind you what EeB-CA2 CSAs consist in. So actually we include some activities such as workshops to establish synergies among the EeB-PPP projects. We also organize some dissemination opportunities in relevant fields. We also set up some trainings and webinars, such as the one today, to help the projects to transfer the technologies. And we also offer some online tools and services to enhance visibility. So the agenda for today's webinar, we will have a presentation of Suscon technologies by Alessandro Lago from SETMA. Then we will have a question and answer time with the audience and a short conclusion by my colleagues from Steinbeiß Europat Centrum. During the webinar, I kindly ask the participants to mute your phone so that we can make sure there will be no disturbing noise during the presentations. And I will be the moderator for the Q&A session, so if you have a comment or a question to raise, just click on the raise your hand button on your screen and I will give you the floor. We will also share the presentations after the webinar. All right.
Okay. So thank you very much. Good morning to everybody. Thanks for attending this webinar. It's a very big pleasure for me to share with you the outcomes of the Suscon project. That was one of the low embodied energy thematic area projects. Before starting, just briefly, some words about SETMA. SETMA is a non-profit research and technology organization dealing with applied research, experimental development, and technology transfer in the field of advanced materials, ICT, and product development. We are located in the south of Italy, in Brindisi, and we are more or less 100 employees among researchers, engineers, designers, and innovation managers. Our premises cover more than 5,000 square meters, and we also have 3 laboratories: the Materials Technology Laboratory, a Virtual Reality Center, and a Rapid Prototyping and Ergonomics Laboratory. This is some of our field of intervention. Our sectors ranges from construction to aeronautics, automotive, medical, safety, and so on. SETMA is structured in 4 main departments: the Material Engineering Department, the Computer Engineering Department, the Design Department, and the Innovation Department. Each department is further composed by several areas, and in particular, the Diagnostic and Civil Engineering area of the Materials Engineering Department was in charge of the coordination of the Suscon project. Very briefly, in the Diagnostic and Civil Engineering area of SETMA, we are 10 employees, 2 civil engineers, 6 materials engineers, 1 architect, and 1 laboratory technician. And we mainly deal with structural reinforcing, non-destructive testing, diagnostic, energy efficiency and recycling, structural health monitoring, and smart materials. So let's come now to the Suscon project. This is the outline of my presentation. After a brief overview of the project, I will describe to you the R&D activities, the industrial upscale and validation, the prototypes and demonstration, before coming to the exploitable results of the Suscon project, and to the LCA, LCC, and HEC analysis, before concluding with the market and economical analysis. So what's the aim of the Suscon project? The aim of the Suscon project was to develop new concepts and technologies to integrate secondary raw materials in the production cycle of concrete. So this will result in a construction product that can be used for ready-mixed and precast application that will be characterized by lightweight, low embodied energy, low CO2 footprint, and improved insulation performances. Some general information. The project starts in January 2012 and lasts for 4 years, so it ended in December 2015. The total budget was about 7 million euro, with 4.5 million euro funded by the European Commission, and it was coordinated by FETMA. Sorry, this slide is not well. Okay, more or less. We were 17 partners coming from 10 countries, 9 EU countries and 1 extra EU countries, and we were 9 R&D performance and 8 companies. So the idea of the SUSCOM project was to take secondary raw materials, to develop new technology to process and transform such secondary raw materials in novel binder and aggregates, and then to combine such novel binders and aggregates from secondary raw material in a sustainable and energy efficient lightweight concrete. The challenges of the SUSCOM project were very ambitious. So the 50% reduction of embodied energy, mainly for the substitution of traditional binder with binder coming from secondary raw materials, the improvement of insulation properties thanks to the use of lightweight aggregates, the reduction of the CO2 footprint up to 50% thanks to the use of secondary raw materials, and as a consequence, a cost reduction and the development of 100% eco-sustainable concrete made with secondary raw materials. The project was structured in 3 levels. The first level was about the development of innovative aggregates and innovative binder from secondary raw material. The second level was about the combination of innovative aggregates with traditional binder, and the combination of innovative binder with natural aggregates. And then the third level was about the combination of innovative aggregates and innovative binder from secondary raw materials into an eco-sustainable concrete made with up to 100% of secondary raw material. So let's go through the development of novel eco-aggregates and binder from secondary raw material. What we have done. We have taken secondary raw material, usually landfilled or incinerated, and developed new technologies and processes to transform such secondary raw materials into lightweight aggregates with improved insulation performances, as you can see here. We have done the same also from the binder side. So we have taken some byproduct, industrial byproduct, so PFA, GGBS, and perlite tailings, and again developed technologies and processes to transform such secondary raw materials into novel eco-binder, what we call geopolymers, that can be used for the replacement of traditionally ordinary Portland cement because of their cost effectiveness, low energy consumption, and reduced CO2 emission. Let's do a step back about what is a geopolymer. A geopolymer is a subset of the alkali activated materials, where for alkali activated materials we call any binder system derived from the reaction of an alkali metal source, the so-called activator, with a solid silicate powder, the so-called precursor. A geopolymer is a subset of the alkali activated materials, where the bonding phase is typically aluminosilicate with low calcium content, and the activator is usually an alkali metal hydroxide or silicate. Okay, so after the development of eco-aggregate and binder from secondary raw material, the next step was the combination of a novel aggregate from secondary raw material with ordinary Portland cement. What we have done. First of all, we have tested the suitability of lightweight aggregates from secondary raw material for the production of lightweight concrete. So we have performed a lot of physical and mechanical characterization, as well as also health safety environmental assessment of the process and product. This table summarizes the main results, but without going so much in the detail. Each aggregate resulted as lightweight with a good particle density. that is essential for a good mix design. Aggregates from secondary raw material also resulted in compliance with chemical requirements and not hazardous in terms of HSE, and this also is a crucial point for a future use in a real application. And then afterward, several lightweight concrete with aggregates from secondary raw material and ordinary Portland cement were designed and tested in terms of workability, air content, fresh density, compressive strength, tensile splitting strength, thermal conductivity, and the UPV test. And at the end, we were able to develop at the lab scale some eco-sustainable concrete made of secondary raw materials and ordinary Portland cement. Next step was the industrial upscaling of lightweight concrete made of traditionally ordinary Portland cement and secondary raw aggregates from secondary raw materials for ready mixed and precast application. At this aim, we set the target performance that we have to obtain for target application that were blocks, panels, and screed, floor-screed and floor-screed underlay. So a parametric study was performed in order to optimize cement content, aggregate content, water to cement ratio, additives, aggregates proportioning, and so on. This is the results we have obtained. So according to the experimental test, a very good mechanical strength were obtained for aggregates like polyurethane and mixed plastic, and very good insulation performances were obtained for all the aggregates used, so polyurethane, plastic scraps, and tire rubber. In conclusion, a successful scaling up from the lab to the industrial level was obtained. Such concretes are suitable for blocks, panel, and insulation component and have a reduced thermal conductivity. In order to evaluate how good were the performances of our lightweight concrete with secondary raw materials, a performance comparison with traditional lightweight concrete based on expanded polystyrene was performed. And as you can see in this picture, lightweight concrete with secondary raw materials aggregates resulted in higher thermal insulation properties up to 3%, and their mechanical performances up to 86% for a concrete based on polyurethane and mixed plastic scrap. Okay, the next step was to check the suitability of the novel binders from secondary raw materials to be used with natural aggregates. At this aim, physical and mechanical and chemical characterization of binders were performed, aiming to investigate the potential for geopolymerization. And a lot of tests were made in order to identify the process parameters for geopolymerization, and this was the main obtained results for PFA and GGBS based binders. And then we developed a geopolymeric concrete made with binder from secondary raw materials and natural aggregates, and tested them in terms of workability, fresh density, compressive strength, UPV test, and durability. Also in this case, we evaluate the chance to upscale such concrete from the lab scale to the industrial plant. So several concrete products were produced by substituting ordinary Portland cement binder with the Suscom binder from secondary raw material for application like facade panel, building blocks, and aerated autoclavated concrete. And as a result, the replicated concrete products were fully conform to existing technical prescription. At the third level, after the development of the novel eco aggregates and binder from SRM, and the combination of novel aggregates with ordinary Portland cement and of novel binders with natural aggregates, the final step was to combine aggregates and binder from secondary raw material in an eco-sustainable concrete with 100% secondary raw material. So Suscon lightweight concrete with aggregates and binder from secondary raw material were designed and tested, targeting specific products like screed, blocks, and panel. All the concretes were developed, optimized in the industrial plant, aiming at optimizing the fresh state and hardness state performances, just like workability, density, mechanical, thermal, and also durability performances, and were performed also HSE evaluation of both raw material and production steps. These are the main results we have obtained on the Suscon products. A very good results were obtained both in terms of compressive strength, it's up to 18 megapascal, and thermal insulation properties, that is 0.16, the lowest. So, innovative concrete based on 100% of secondary raw material from both the aggregates and the binder side were successfully optimized for ready-mix and precast application and resulted with improved insulation performances, and also resulted as not hazardous after an HSE analysis of raw materials and both production processes. Afterwards, several Suscon precast components, so blocks, panels, were manufactured in the plant with the aim of testing the performances in terms of mechanical resistance, thermal and acoustic insulation, and fire resistance. One of the main achievements of this upscale was that the Suscon product production are highly compatible with the existing concrete production processes, so minimized equipment costs are required. In this slide are included some pictures of the industrial production. More than 1,000 Suscon blocks and 50 Suscon panels were produced and tested. In terms of characterization of such prototypes, we found that the Suscon blocks have a reduced U value that is half of the reference block, commercial block, and the Suscon panels have an improved fire resistance that is 4 times higher than the reference commercial panel. Suscon panel have fire resistance that is IE to 240, while reference commercial panel have a fire resistance that is IE 60. We also performed numerical simulation of Suscon prototypes exposed to realistic environmental conditions, and we were able to conclude that Suscon prototypes allow a thickness reduction up to 88% with the same thermal insulation, and a lower consumption up to 10% compared to normal concrete. Let's come now to the exploitable results of the Suscon project. At the end of the project, we were able to develop 3 construction eco-sustainable products, namely floor screed, building panels, and building blocks. For each type, data sheets were compiled, including all the main characterization, physical and mechanical characterization we have made. So this is the data sheet for the floor screed, and this is the data sheet for the building panel, and this is the data sheet for the building blocks. For each product, we have several types of Suscon components, as we have used different type of aggregates, such as different type of binders. So, for example, at the end of the Suscon project, we had 5 types of blocks and 2 types of panel and 1 type of screed. final step was the demonstration in real scale demo site. We have the chance to validate the SASCON outcomes in 3 European regions, in Spain, in EeB, in Turkey, and in Romania, as you can see in this picture. This is the demo in Spain, where we use SASCON blocks, the SASCON panels, also reference mock-ups made with traditional commercial available building components were constructed, so in order to make a comparison also during the service life. This is some picture about the installation in Romania of both panel and blocks, SASCON blocks and panel. And this is some picture about the installation in Turkey. We performed some monitoring for the mock-ups in order to evaluate the in-service installation performances of our SASCON project, and we developed some testing procedure in order to evaluate the global thermal efficiency of the new structure, as well as to compare acoustic installation of SASCON product with the reference one. And in the end, we were able to verify that SASCON products have improved the thermal insulation with respect to commercial available reference product and comparable acoustic insulation performances. We have also performed some LCA, LCC analysis in order to evaluate the impact and the sustainability of the SASCON project for future application in the industrial plant. So according to the LCA analysis, there are some SASCON products that can meet the target of the 50% CO2 reduction with respect to reference products and reference recipes based on ordinary Portland cement. Again, according to the LCA analysis, the SASCON product meet the reduction of the 50% of embodied energy with respect to traditional commercial product. And we have performed also a life cycle cost analysis in order to evaluate the global costs for the production of the new SASCON product from raw material to the production. And in the end, we were able to verify that the SASCON product can meet the target of the reduction of 50% of the cost with respect of traditional commercial products with the same installation performance. According to the HAC analysis, all the SASCON products are non-hazardous and non-toxic, both in terms of raw materials and processes. And this is another exploitable result of the project. We have made available it on the website. We have called it SASCON tool. It is a sort of app you can use in order to get information on secondary raw materials in different EU areas in terms of amounts, trends, and regulation in different European region. You can find also a database with the SASCON recipes and their performances. And it can also be used as a mixed design tool for SASCON recipe. So with two main characteristics, you can perform performance-based design in terms of density, thermal conductivity, strain, but also the traditional volumetric design. We have finally made a market analysis of our SASCON product. Unfortunately, the graph cannot be seen in this picture, but what is important is that the payback period for SASCON geoscred is after 2.5 years, while for SASCON block, the payback period is after 4 years, and for SASCON panels, the payback period is after 2.8 years. Okay, so let's come now to the main achievement of the project. The main aim of the SASCOM project was to develop sustainable, innovative, and energy-efficient concrete using secondary raw material. At this aim, several eco-sustainable concrete recipes based on innovative aggregates and binders from secondary raw materials have been suitably designed and developed, targeting specific products just like blocks, panels, and screeds. And 50 panels and 1,000 blocks for precast application and ready mixed, so screed SASCOM prototypes have been industrially produced and tested, resulting in a reduced U value that is half than the reference commercial blocks, in improved fire resistance that is 4 times higher than reference commercial panels, and a comparable mechanical performance. The SASCOM solution were installed on 3 real-scale demo buildings in Spain, Turkey, and Romania, resulting in improved thermal insulation performances in service and comparable acoustic insulation performances. SASCOM product met the target reduction of 50% of CO2 emission, 50% of embodied energy, and 15% of cost. SASCOM products and processes are not hazardous after the HSE evaluation, and SASCOM products are highly compatible with existing concrete production processes, so minimize the equipment costs are required, and the payback period is after in the range of 2.5 to 4 years. And last but not least, we have verified the high replicability of the SASCOM outcomes using local materials from different sources for the demonstration activities. This was the theme of the SASCOM project. This is with the blue t-shirt, it's me. And if you need any further information, you can visit the SASCOM website or just send me an email to this address. Okay. That's all from our side. Thank you very much.
Okay, thank you very much, Alessandro, for this very comprehensive presentation. I will now open the question and answer session. So if there is any comment or question from the audience, please raise your hand. Yeah, a first question by Jürgen. Please, Jürgen.
Hello, Alessandro. A very interesting presentation. I have a question for the fire resistance of the products, because you mentioned that there are a lot of organic materials inside, so it must be maybe a trick. It must be tricky to get a good fire resistance. In which glass which glass, fire resistance glass, could the material reach?
Okay. Hi, Jürgen. It's very nice to hear you after some months. The SASCOM panel can reach the fire resistant class of IE-240, while the traditional commercial reference panel we have used for comparison can reach the IE-60 fire resistant class. So for SASCOM product, we have reached 4 times higher fire resistance.
Okay.
This very nice presentation. It was very interesting, and actually I have some questions regarding exploitation, because I have found that you have very nice findings in this project, and I would like to know if you have planned some protection on the results, patenting, and if you are planning maybe to take some contact with industries, because I think this would be really a pity if these really nice results are not going on the market.
Yes, thank you for your question. At the end of the project, if I remember well, we have listed 40 to 50 exploitable results. So there are a very quite huge number of exploitable results for our industrial company. But we have decided not to patent any any outcome of the project, because according to one of our industrial partner, if I remember well, it was BASF. It's very easy to, let's say, to overcome a patent about a concrete recipe, because you can just slightly modify one component of the proportioning. So we have followed their suggestion not to patent. But for sure we are in contact with both the industrial partner of the SASCOM project, but also with other industrial partners. We are using the outcome of the SUSCOM project to join other European funded projects. We are working a lot on the results being built on the outcome of the SASCOM, because we see two great exploitable potential for this. One of the main outcomes of the SASCOM is that you can obtain the same, more or less the same performances for the SASCOM project at the industrial plant by using different type of secondary raw material coming from different sources. And I think that it is a great chance to exploit these results all along Europe. We had a great problem with Turkey, because they did not allow the material, secondary raw material coming from other places in Europe to come into Turkey, and so we were obliged to find local material in order to produce prototype and demonstration. But I think that is one of the main outcome of the project. So you can produce SASCOM products and components using every secondary raw material available all along Europe.
Well, thank you for this answer. It is very interesting anyway, and I hope this will be anyway in the future on the market.
I hope too.
Thank you.
You're welcome.
Thank you. Any other comment or question? Jürgen? Yes, please.
No, it's okay.
No, okay, because I had still your hand raised.
Oh, sorry.
Okay, so, well, if there is no more question or comments, let's go to the conclusions from my colleagues. Here.
Thank you, Anne-Claire, and also thank you, Alessandro, for this very interesting presentation. This is Franziska from Steinbay, and I would just like to give you a brief follow-up on the activities EeB-CA2 is still implementing until its end, its completion by the end of January. I think a few of you have already heard what we are doing. So one activity where you can also get involved in is to actually have a booth at the ECTP conference. Here you can see in the slides the different offers, what it costs, and if you're interested in that, you can actually click on the link that you can see in the bottom of the slide, or contact Anne-Claire directly for that. And the ECTP conference will take place in Brussels on 17th and 18th of November. Anne-Claire, can you change to the next slide? Okay. So another activity also happening during the ECTP conference is the EeB matchmaking event. It's going to happen on Friday afternoon, so on the 18th, and this is a free of charge event. You don't have to actually attend the ECTP conference in order to attend the EeB matchmaking event, but you can do both. And it's a good way to book in advance bilateral meetings with other participants in order to exchange on new collaboration ideas such as research projects, commercial cooperation, or some sort of investment, for example. And the booking is now open. You can also already start booking of bilateral meetings, and you can just follow the link in order to participate and register yourself. Then we offer the EeB-CA2 coaching service, which is the so-called innovation assessment. This is an assessment where we analyze with you your innovation strategies towards a certain technology that you, for example, developed in one of the EeB projects you're involved in. This is an activity that we can individually do with all the different partners of a project. So we're not looking only at the project, but also at the partner and their organization and their own strategy towards innovation. And we will give you an assessment sheet that you will return to us. We will analyze it and also provide you a report on that. So if you're interested in that, you can contact me or also my colleague Sandrine Doretto. And if you haven't done so, please feel free to join our LinkedIn group. It's called the ECTP Energy Efficient Buildings Committee. You can also see the link below. We already have nearly 800 members in the group by now, and it's a good way to provide, for example, your own public deliverables or newsletters or exchange on upcoming events and discussions. So it's on the one hand a good way for you to provide your data to the community, or also to get informed about other activities that are being implemented by the whole community and other EeB projects.
And yeah, that's it. So we will close the webinar here, and I wish you a nice day.
Have a nice day too. Thank you very much.
Goodbye. Thank you.
Bye.
Goodbye.